Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module D2A Converter from paper measurements and instrumentation. So students, let us see what we are going to learn in this module. In this module, the concept of digital to analog and analog to digital conversion is explained. The D2A conversion using variable resistor networks is explained. The expression for analog output voltage obtained using the variable resistor method is derived. Finally, binary ladder or R2R ladder for D2A conversion is discussed and the expression of gain is obtained. An analog system contains devices that manipulate the physical quantities represented in analog form. In an analog system, the quantities vary continuously over a range of values. For example, the amplitude of output signal from the speaker of the radio receiver can have any value lying between 0 and a maximum limit. A digital system is the one which takes only discrete values, that is, it is a combination of devices designed for manipulating physical quantities or information which is represented in digital form. For example, calculators, digital watches, etc. Digital systems are much preferred over analog ones, as the storage of information is much easier because of the special switching circuits that can latch into information and hold it for longer periods. Also, they provide greater accuracy and precision, as the digits of precision can be increased by adding more switching circuits. On the other hand, in analog systems, precision is limited as the values depend on the circuit components. In addition, digital circuits are less affected by noise. Despite numerous advantages of digital systems, the main drawback of using digital techniques is because of the fact that the real world is analog. That is, most physical quantities are analog in nature. Therefore, in order to take advantages of digital techniques while dealing with analog inputs and outputs, there is a need for digital to analog, that is D2A, and analog to digital, which is A to D conversion. For example, to process a physical quantity, the following steps are needed. First, convert the real-world analog inputs into digital form. Second, process the digital information. Third, convert the digital outputs back into analog form. Last, such conversion between analog and digital quantities has become quite common in current technology because of the increasing shift towards digital techniques, and is thus discussed in this module. For example, to process a physical quantity, the following steps are needed. First, convert the real-world analog inputs into digital form. Second, process the digital information. And finally, convert the digital outputs back into analog form. Such conversion between analog and digital quantities has become quite common in current technology because of the increasing shift towards digital techniques, and is thus discussed in this module. To analog and analog to digital conversion. Digital to analog, which is also known as D2A, and analog to digital, also known as A to D conversion, form two very important aspects of digital data processing. Digital to analog conversion involves the translation of digital information into equivalent analog information, and this is accomplished with the use of digital to analog converter, which is also known as DAC. DACs are used whenever the output of a digital circuit has to drive an analog device. In this respect, a D to A converter is sometimes referred to as decoding device. The process of changing an analog signal into an equivalent digital signal is accomplished with the help of analog to digital converter, which is also known as ADC. For example, an A to D converter is used to change the analog output signals from transducers, which are measuring, for example, temperature, pressure, etc., into equivalent digital signals. Since the function of ADC is to encode signals for entry into a digital system, it is sometimes called an encoding device. Digital to analog conversion is a straightforward process and is considerably easier than A to D conversion. In fact, a D to A converter is an integral part of A to D converter. Therefore, we will first consider the D to A conversion process. D to A conversion is the process of taking a value represented in digital code, such as simple binary or BCD as input, and converting it into a voltage or current which is proportional to the digital value. The basic function of a DAC is shown in the figure, where the DAC can have n number of digital inputs, and corresponding to that there is a single analog output V output. The circuit of a DAC consists of a resistor ladder network, a reference precision voltage supply, logic inputs, and an operational amplifier. Depending on the type of ladder network, there are various techniques which can be used to realize a digital to analog converter. The most commonly used techniques are discussed as follows. The first one is the variable resistor networks. In this method, D to A conversion is accomplished by designing a resistive network that will change each digital level into an equivalent binary weighted voltage or current. To understand the meaning of equivalent binary weight, consider a 3-bit binary signal which has 8 possible digital signals. Our aim is to convert the 8 possible digital signals into equivalent analog voltages. Let us choose the voltage range of analog signal to be developed to lie between 0 and plus 7 volts. Therefore, the smallest digital level, which is 000, can be thought of to be equal to 0 volt. And the largest digital level, which is 111, can be thought of to be equal to plus 7 volt. In between 000 and 111, there are 7 discrete levels to be defined. Thus, the analog signal is divided into 7 levels. The smallest incremental change in digital signal is represented by the least significant bit, that is LSB, which corresponds to 2 to the power 0. This should introduce a change in analog output equal to 1/7 of the full scale. Hence, the resistive divider is designed in such a way that a 1 in the 2 raised to power 0 position will result in plus 7 into 1/7 equals plus 1 volt at the output. Since 2 raised to power 1 corresponds to 2, which is twice that of 2 raised to power 0, which equals 1. Thus, a change in the 2 raised to power 1 bit position must cause a change in analog output, that is twice the LSB. The resistive divider must be constructed such that a 1 in the 2 raised to power 1 bit position will cause a change of plus 7 into 2 by 7 equals plus 2 volt in the analog output. Similarly, 2 raised to power 2 is equal to 4, which equals 2 into 2 raised to power 1, which also equals 4 into 2 raised to power 0, which means that 2 raised to power 2 bit must cause a change in output voltage equal to 4 times that of LSB. The resistive divider must be designed such that a 1 in the 2 raised to power 2 position will result in a change of plus 4 volt at the output. Thus, each successive bit must have a weight that is twice that of the preceding bit. The binary equivalent weights for 3-bit and 4-bit digital signals are tabulated in the table below. It should be kept in mind that the sum of binary equivalent weights must equal 1. For the 3-bit input, the weight corresponding to the 2 raised to power 0 bit, which is LSB, is given to be 1 divided by 7. The weight corresponding to 2 raised to power 1 bit is 2 by 7, and the weight corresponding to the 2 raised to power 2 bit is 4 by 7. Similarly, the binary weights corresponding to the 2 raised to power 0 bit in 4-bit digital signal is 1 by 15, corresponding to 2 raised to power 1 bit is given by 2 by 15, and 2 raised to power 3 bit is given by 8 by 15. In general, the binary equivalent weight assigned to the LSB is 1 divided by 2 raised to power n minus 1, where n is the number of bits. The change in output voltage due to change in LSB is equal to V divided by 2 raised to power n minus 1, where V is the digital input voltage level. The remaining weights are then found by multiplying the weight of LSB by 2, 4, 8 and so on. In the following table, we have calculated the analog outputs for 3-bit digital input by using the binary equivalent weight of the corresponding bits. That is, let us say for an input of 001, then the binary weight corresponding to 2 raised to power 0 bit is 1 by 7. So 1 by 7 into the digital input voltage level, which is 7, resulting into the analog output of plus 1 volt. Similarly, the digital input of 111 will give an analog output of plus 7 volt. Let us now see that how to draw a resistive divider corresponding to the analog outputs obtained from digital inputs. To draw a resistive divider that changes the digital signal into equivalent binary weighted voltage, the network should have 3 inputs, that is, the digital inputs are 2 raised to power 0, 2 raised to power 1 and 2 raised to power 2, and one analog output V output, which is shown in the figure. The following conditions must be met by the resistive divider. First, the 2 raised to power 0 bit must give plus 1 volt analog output, and 2 raised to power 1 bit must give output voltage of plus 2 volt. Similarly, 2 raised to power 2 bit must give an output of plus 4 volt. The sum of these 3 voltages representing the digital bits must form the analog output voltage. The resistive divider corresponding to 3-bit digital input that satisfies the above mentioned conditions is shown in the figure A below. As can be seen in the figure that the resistors R0, R1 and R2 form the divider network. RL is the load resistance to which the divider is connected. RL is taken to be much larger than R0 so that it does not load the divider network. Assume that a digital input signal 001 is applied to the resistive ladder network. The equivalent circuit is shown in the figure B. As discussed before, digital 0 means 0 volt and digital 1 means plus 7 volt. The analog voltage VA can be found by the use of Millman's theorem. Millman's theorem states that the voltage appearing at any node in a resistive network is equal to the summation of currents entering the node divided by the summation of conductances connected to the node. In equation form, it can be expressed as V is equal to V1 by R1 plus V2 by R2 plus V3 by R3 plus so on divided by 1 by R1 plus 1 by R2 plus 1 by R3 plus so on. For the equivalent circuit, which is described in figure B, it can be expressed in equation form as VA is equal to V0 by R0 plus V1 divided by R0 by 2 plus V2 divided by R0 by 4 divided by 1 by R0 plus 1 by R0 by 2 plus 1 by R0 by 4, which equals 7 by R0 divided by 1 by R0 plus 1 by R0 by 2 plus 1 by R0 by 4. This results in VA being equal to plus 1 volt. The above equation can be expressed in modified form as VA is equal to V0 by R0 into 2 raised to power 0 plus V1 by R0 into 2 raised to power 1 plus V2 by R0 into 2 raised to power 2 on the whole divided by 2 raised to power 0 by R0 plus 2 raised to power 1 by R0 plus 2 raised to power 2 by R0. Thus, this can be simplified to obtain VA to be equal to V0 into 2 raised to power 0 plus V1 into 2 raised to power 1 plus V2 into 2 raised to power 2 on the whole divided by 2 raised to power 0 plus 2 raised to power 1 plus 2 raised to power 2. The further simplification will lead to the expression VA equals V0 into 2 raised to power 0 plus V1 into 2 raised to power 1 plus V2 into 2 raised to power 2 divided by 2 raised to power 3 minus 1. So we can write in general VA is equal to V0 into 2 to the power 0 plus V1 into 2 raised to power 1 plus V2 into 2 raised to power 2 plus so on till Vn minus 1 into 2 raised to power n minus 1 divided by 2 raised to power n minus 1. Here V0, V1, V2 till Vn minus 1 are the digital input voltage levels and n is the number of bits. In the similar way, we can draw the equivalent circuits for the remaining 7 input combination and apply Millman's theorem to obtain the corresponding analog voltages as shown in the table discussed before. So, the criteria for drawing a resistive divider network to convert digital data into analog data may be summarized as follows. First, there should be one input resistor for each digital bit. Second, beginning with the LSB, the value of each following resistor should be 1/2 the size of the previous resistor. Third, the full-scale output voltage should be equal to the positive voltage of the digital input. The use of resistive divider network in digital to analog converters is limited due to its two main drawbacks. Firstly, each resistor in the network has a different value. There is a large difference in the values of resistors corresponding to LSB and MSB, especially when the number of bits is large. Using the current IC fabrication technology, it becomes very difficult to produce resistors of values over a wide range that maintains an accurate ratio, especially with change in temperature. Also, being the precision resistors, they add a lot to the expense and are thus not preferred. Secondly, the resistor used for the MSB is required to handle much larger current than that used for LSB. For example, in a 10-bit system, the current through the MSB resistor is 500 times that through the LSB resistor. Because of these shortcomings, it is preferable to make a circuit which uses fairly close values of resistances. One of the widely used EAC circuits that overcomes the drawbacks of variable resistor network is the R2R ladder network, which is also known as binary ladder. In this network, the resistors used have only two values, which are in the ratio of 2:1. Let us now discuss the binary ladder or the R2R ladder. The binary ladder is a resistive network whose output voltage is a properly weighted sum of the digital inputs. The circuit of a binary ladder for 4-bit digital input is shown in the figure below. The left end of the ladder terminates in a resistor of 2R, and let us assume that the right end, which is the output, is open circuited. We will first study the resistive properties of the network, assuming that all inputs are at ground. Considering node A, the total resistance looking back into the terminating resistor is 2R, and the resistance looking out towards the 2 raised to power 0 input is also 2R. These two resistors can be combined to form an equivalent resistor of R, which is shown in figure B. Now, at node B, again, the total resistance looking from node B down the branch towards node A is 2R, as is the resistance looking out towards the 2 raised to power 1 input, which is shown in figure B. Now, these two resistors can be combined to give a simplified circuit, which is shown in the figure C. Now, at node C, the total resistance looking into the branch towards node B is 2R and is equal to that looking out towards the 2 raised to power 2 input. On simplification, the circuit in figure C will reduce to that shown in figure D. In this circuit, the resistance looking back towards node C is 2R and is equal to the resistance looking out towards the 2 raised to power 3 input. Thus, it is seen that the total resistance looking from any node back towards the terminating resistance or out towards the digital input is 2R. The above statement holds even when the digital inputs are at plus V volts. This is because the digital inputs are assumed to be ideal voltage sources, and internal impedance of an ideal voltage source is 0 ohms. The resistance characteristics of the ladder can be used to find the output voltages for the various digital inputs. Let us first find the analog output voltage due to MSB. Consider that a signal of 1000 is applied to the inputs. The corresponding binary ladder is shown in the figure below. It can be seen from the figure that there is no voltage source to the left of node D. Therefore, as explained earlier, the entire network to the left of this node can be replaced by an equivalent resistance of 2R, resulting in the equivalent circuit as shown in figure B. The output voltage VA can be determined using the voltage divider rule as VA equals V into 2R divided by 2R plus 2R. This makes VA to be equal to V by 2. Thus, a 1 in the MSB will produce an analog output of V by 2 volts. To find out the output voltage due to second MSB, assume that a digital input of 0100 is applied as shown in the circuit in figure 6a. Since there are no voltage sources to the left of node C, therefore it can be replaced by an equivalent resistance of 2R as shown in figure 6b. The circuit to the left of node C can be replaced by its Thevenin equivalent having a resistance capital R in series with a voltage source of plus V by 2 as shown in figure 6c. Now using the voltage divider rule, the value of VA is obtained to be VA equals plus V by 2 into 2R divided by R plus R plus 2R. This gives VA to be equal to plus V by 4. Continuing in this way, the output voltage due to third MSB and fourth MSB can be derived to be plus V by 8 and plus V by 16 respectively. The table shows the binary weights and analog voltages corresponding to various bit positions. It can be inferred from the table that each digital input is transformed into a properly weighted binary output voltage. The total output voltage due to a given input will be equal to the sum of the output levels due to each digital input separately. Thus, net output voltage due to capital N bits in the input is given by VA equals V by 2 plus V by 4 plus V by 8 plus V by 16 plus so on till V divided by 2 raised to power N. Or equivalently, we can express VA equals V0 into 2 raised to power 0 plus V1 into 2 raised to power 1 plus V2 into 2 raised to power 2 plus so on till Vn minus 1 into 2 raised to power n minus 1 on the whole divided by 2 raised to power n. Here V0, V1, V2 till Vn minus 1 are the digital input voltage levels. Equation 4 can be used to find the output voltage from the ladder for any digital input signal. It is important to note that the expression for output of binary ladder, which is given in equation 4, is same as that of resistive divider method, which is in equation 3, except the term in the denominator. The slight difference in denominator makes this method clearly different from the resistive divider method. The full-scale output voltage for the binary ladder is given by VA equals V into, within the brackets, 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 and so on till 1 by 2 raised to power n. The terms inside the brackets form a geometric series whose sum will approach 1 only if the number of terms are sufficiently large. However, it will never be equal to 1. Thus, the full-scale output voltage of the ladder approaches V only in the limit. On the other hand, in the resistive divider method, full-scale output voltage is always equal to the voltage level of the digital input. Note that in the binary ladder, the output is terminated in a resistance of 2R. Although this will result in a lowering of output voltage, but it is important to keep the ladder in perfect balance. If the load 2R is maintained constant, the output voltage will be weighted sum of the binary input bits. Else it will not be a properly weighted sum. Also, as already discussed, by terminating the output of ladder in a load of 2R, The input resistance to the ladder seen by each of the digital voltage sources is constant. This will overcome the limitation of resistive divider as the digital voltage sources can be designed for the same load. So students, let us now summarize what we have learned in this module. In this module, the concept of digital to analog and analog to digital conversion was explained. Then, the digital to analog conversion using variable resistor networks was explained. The expression for analog output voltage obtained using the variable resistor method was derived. Finally, the binary ladder or R2R ladder for digital to analog conversion was discussed and the expression of gain was obtained. Thank you students for your attention.